Is fairly audible, sir.
And you can see my screen, right?
Yes, yes, absolutely. Presentation we can see. It's 10 o'clock. I think we can start. Or till now we have only 23 participants. So
We
if
can wait for a little bit if you want. I'm fine.
okay, sir. So we can wait. I think five more minutes. Participant, you can ask your colleague to join so we can start. Good morning and welcome back on this fifth day of 5-day FDP on advanced research capabilities in architecture and planning. We hope you all had restful evening and ready for another day of learning and exploring. Before we start, let me introduce myself. My name is Divya, working as an assistant professor in Faculty of Architecture Planning. As in, I'll be the rapporteur for today and tomorrow's session. In this journey of understanding research technique, we are able to, till now, we are able to comprehend how to justify, illustrate, do chapterization of a research report, how to identify research gap, how to do SLR, what is research design, what is qualitative research method. We had very insightful session by our esteemed speaker on various aspects of research in architecture and planning in last 2 days. Today, we have an exciting lineup of speakers who will share their experience and expertise on different topics of research methodology approaches. I think we had 39 participants, so we can begin with the session. Uh, Today, good morning everyone again. Welcome for the third day of FDP on advanced research capabilities in architecture and planning. We are delighted to have with us today Dr. Joydeep Datta sir. After his insightful presentation on finding research gap on day one, we are now eager to hear from you again today morning and learn from your knowledge on sampling design. Before we begin the session, I would like to remind you all, as part of my duty, that 100% attendance is mandatory, and please keep your microphone mute during the session. We welcome you, sir. To begin this session, over to you, sir.
Okay, thank you very much for inviting me again. Welcome and good morning, everyone. Today we have to put on our quantitative caps largely, as I understand that this one and the next presentation and the one after that, they will mainly be about quantitative research, and research design has already been spoken to, and qualitative also has been taken care of. Today, we have a day of quantitative, and we're starting with sampling design. Okay, the theory and methods of sampling design. It will presuppose that you know some concepts of research design, like concepts, variables, measurement scales, and all of that. But still, I'll try to take you through it as if it is a clean slate, at the risk of repeating what some of the speakers may have already spoken about or will speak to you about later. So if we dig deep into the idea of sampling, we essentially get the basic concept as this. Suppose, and I'll start with examples and I'll finish with a relatively elaborate example. So I think that's a good way to learn and remember. Suppose you want to find out the average income of families living in a city. Okay. So just imagine the amount of effort, time, money, and resources required to go to every family in the city to find out their income. That's almost impossible, right? Impracticable. So instead, you select a few families to become the basis of your inquiry and gather information about their average incomes. That is possible. So a few families, but we have to select them. Then, from what data you collect of these few families, you make an estimate. Okay, some kind of an estimate. It may be an average, it may be some kind of a function of the indicators. You make an estimate of the average income of the families of the entire city. So you are actually finding out things about a few families, but then you will deduce from it, or you will induce from it, that similar is the average income of families of the entire city. This process, okay, of, instead of counting all families, you count a few families, is called sampling. It's as simple as that. So if we see it graphically, let's say you have a study population, okay? The entire universe of the people that you want to examine or find out about. It may not be people, it may be schools, okay? It may be nations, it may be anything. But let's say the study population is made up of small sampling elements, okay? So you have a lot of these elements. In our example, this is all the families in the city, okay? So each family is a sampling element or unit, right? So from that, like we said, you select a subset, okay? A subset of a few sampling elements from the study population. From the large one, you select a subset, and that we call a sample, okay? And in that sample, you will have these few families that you have selected, which you think is a manageable amount of work that you can do, okay? So then you collect information from these few families, the sample, to find answers to your research question. And then from that, you infer. It may be induction, it may be deduction kind of logic, but from these sample findings, you make an estimate of the prevalence of the same characteristics in the study population. So we do it for a small bit and we infer that that holds true for the whole thing. Simple biological example is that you're not well today, okay? You have a fever and a cold and you're shivering. And the chances are that you have malaria. So you ask for a test and the path comes in and he takes a sample of your blood. Of course, he won't take your entire blood to find out if there is a malarial parasite throughout your body, right? Takes a sample, a small bit, and then takes it to the lab, finds out about it, finds out whether the malarial parasite is there or not. He will be having some kind of a mechanism or an experiment to find it out. And then if he finds out that yes, it is positive and there is malarial parasite in that small amount of blood that you gave, then they will infer back saying that, well, your whole blood cycle within your body, because they are continuous to each other and contiguous and all of that, has malarial parasite, and so you have malaria, and so you need to have the medicine. If in that small bit there was no malaria found, then we assume automatically, logically, that the whole blood sample or the whole amount of blood in your body has malarial parasite or not. So the test that you do in the lab and the finding about that small sample is called the sample statistic. Not statistics, but statistic. And so that same characteristic, that yes, malaria, no malaria, when you infer back to the entire population, okay, then it's called the population parameter, and the difference between the sample statistic and the population parameter is called the sampling mean, like the sampling error, okay? Okay, population parameter is sometimes also called population mean, but as long as you understand the concept, what exact terminology you are using is not so important. So from the small sample, the subset, the characteristic that you find out is the sample statistic, and when you infer that to the larger population, it's called the population parameter. However, because at the end of the day, we are guessing, we are predicting, we are only estimating or guesstimating, there will be a difference between what you estimate and what will be the parameter. So a better example in this case is, what is the average family income? And you extend that to the average family income of everybody in the city. That's the basic concept. As simple as that. Yeah. So what is sampling? What is sampling? Sampling is a process of selecting a few elements or samples from a bigger group, which we have called the sampling population, to become the basis for estimating or predicting unknown information or outcome regarding the bigger group. This is the formal way to define it. What's the advantage of sampling? Well, it saves time as well as financial and human resources. It makes it realistic. You can't always do for the entire population. And what is the disadvantage? Obviously, you do not find out information about the entire population's characteristics, right? After all, you only estimate or predict them based on a small sample. So there is a possibility that error will exist in your estimation. Basic. So it's a trade-off, the sampling. The trade-off between time saving, resource saving, making the study feasible, and compromising the level of accuracy in your finding. There are some technical terms which will be elaborated in the next 2 sessions today, I'm sure, when you talk about hypothesis and stuff like that. But the level of accuracy is a key phrase that you may note down or remember. If we go on, we're going to say or discuss that if your method of sampling, there will be error. Okay? But if your method of sampling is systematic and correct, your findings should be reasonably accurate. Reasonably accurate. But errors do occur. So there is discrepancy or difference between the characteristics of the sample and the population. Recall, the characteristic of the sample is the sample statistic, and the characteristic of the population we'll call the population parameter. There is a discrepancy. But statistical analysis will minimize the probability of these errors. And it will not just minimize, it will also estimate how wrong it can go. Okay? So it will minimize and even estimate the probability of these errors with a certain degree of surety. That I'm almost sure. So what is the confidence level? That is another technical phrase that you need to remember. Okay, the confidence level. That is the degree of surety with which you can say, yes, I may go wrong, but I won't go wrong beyond plus minus 5%. Okay, then your confidence level is 95. If you're doing something more specific, okay, you want to say plus minus 2%. Yeah. So this level of tolerance of the error, how much of error can you tolerate? Okay, is the level of significance that also becomes important in selecting a sample. Okay, so when we select a sample, we need to find out basically by which method do we choose the sample. We'll try to learn it today. And what should be the sample size, the size of the sample that we choose. Okay, we'll touch upon it because it is more mathematical. I don't think we need to get into depth of how to find the sample, but there are standard industry practices, some research benchmarks that you need to follow, and we'll do that with an example. Right? So before we get into an example, let's go through the terminology. We've already used some words, some terminology. So again, in the previous example, okay, all the families living in the said city, all the families in the city are called the population or the study population. The small group of families that you chose to collect information from is called the sample. The actual number of families you chose, the number of families, how many did you choose? 10, 100, 1,000? That is the sample size, the actual number of families. And the way you identify and select these families is the sampling design. Okay? How did I choose it? What rationale did I use? That is sampling design or sampling strategy. Like we said, okay, each individual chosen family is the sampling element, and every member of the family is a population element. Okay, it may be single or composite. We could have done it for individuals, which would be single. We could have done it for families, which we are doing now, which is actually a composite, but we are taking it as a single. It can be taken by wards, it can be taken by districts, and it can, but it should be consistent. Then you come to another important term called stratum. Okay. Stratum, which means layers. Okay. So stratum is a subset of a sample made up of some elements that share some characteristics. The meaning of the word stratum is layers. Okay. So what are you layering actually? Okay. That we will find out, or how we do it when we use stratified sample. That's the word will come. So that comes from stratum, which means layers. And these layers are nothing but some common elements which are shared. Like say, we say that, okay, we are finding out for families, but whether it's a joint family or a nuclear family has a huge, real impact on whatever we are finding out, which is the average family income. So we have to keep it separate. Okay, we cannot compare the average income of joint families with nuclear families. Joint families essentially meaning more than one person actually earning. Okay, so or we could stratify it by ward or geographic area. Okay, so that is some kind of a layering that we look at. Okay, so another word is sampling frame. What is this? Well, an existing list identifying every family in the city may be there. Maybe you have a voters list, or maybe you have a list, okay, which says the below poverty line list. Now, the below poverty line list automatically is a subset of all the families. We are only taking the so-called poor family. How do we operationalize this word poor? Okay, maybe the government of India has set a benchmark. Below this per capita is poor, and they will be entitled to some benefits, XYZ, and above that is not poor. So that is the sampling frame. So if you're trying to find out something about the BPL families, that is your sampling. Okay, if you're trying to find out about digital literacy, say, digital literacy of senior citizens. Okay, parents and grandparents are bad with smartphones. All right, we're trying to find out how much is their digital intelligence or their digital ease of use. Well, we can actually take a list of all the people who bought SIM cards. That is a good sampling frame for that kind of a research study. So it may or may not be there. You may have a list which may be incomplete, and it's not mandatory to have a list, but if you have it, then that's called the sampling frame, which is in a way a subset of the sample, but a subset of the population, the sampling frame, but it's a superset of the sample itself. We'll see examples as we go on. So your findings based on the information. So the information you took from your selected families is the average income of the family. Based on the information obtained from your respondents are the sample elements, are called the sample statistic. So that is the characteristic you'll find out. In this case, it will be a figure, rupees, okay, maybe per year or per month. Now, if some of your enumerators, the people who've gone out to survey for you, have found out for the year, and if some have found out for the month, if some have actually found out for the week, then they have to be adjusted, and we need to know or operationalize the sample statistic, but that is what we found out. But your ultimate aim is not to find out the average family income of those people. It is to find out for the whole family, right? So you use the sample statistic. Here I've used the word statistic because it may be 2 or 3 parameters that I get out, or 2 or 3 sets of information. So you use the sample statistic or the number of statistics that you have, okay, the average family income of the entire society, okay, which will be called the population parameter. So when you infer back saying that this is the average family annual income, see, I've used the word annual, I have restricted, I have operationalized, I have set a working definition onto that particular assumption of ours. So that is the population parameter. And as we said before, the difference or the discrepancy between the statistic and the parameter is called the sampling error. To select an unbiased sample, now we'll come to the idea of bias, okay? Because we will talk about randomness and chance and probability. So to select an unbiased sample, each unit should have an equal and independent chance of getting selected into the sample. So equal and independent chance of actually selecting the right or the proper ones. Okay, how effectively do I choose that subset? Okay, that needs to be unbiased. And if it is unbiased, then each unit should have equal chance, which means that everyone has a chance to be selected. And an independent chance. Just because my wife was selected doesn't mean I will not be selected. Just because one person from my housing apartment has been selected, it doesn't mean that I will not be selected. So every element, be it a family or an individual, has equal and independent chance of being selected. That is the idea of randomization, because we'll work with probability. Okay, so randomization is an idea that you need to put in, and because of randomization, we can surmise or we can assume that we will have a relatively unbiased sample, and thus we will have a relatively accurate prediction of the population parameter from the sample statistic. Okay. So sampling error, now sampling error also has some elements to it. So if we can graphically take a look at it, it'll look like this. This is your entire population, okay? The study population. And this is your subset, let's say the sample. Well, remember we had something called the sampling frame, which was a proxy indicator of the population. Actually, a sampling frame is a list or a telephone directory list or something like that, which helps to get in touch with the respondents, the families, maybe their contact numbers or something. But it is not necessarily the entire population, because a lot of them will not be there, okay, on the list. So there's a sampling frame that comes in between the population and the sample. And then there is another little subset of the sample, which is actual responses. Well, you may have gone to each of these families, but each of the families either may not have been available or did not want to give you the data. Which means that if you had a target sample size of 1,000, you went out to do it, and maybe everyone is not coordinated. You have 10 people doing it for you. They are spread all over. And they come back and said, well, let's see how much who's got. And we've done this exercise many a time. You see that finally you have 850. Or that's a good number. Let's say you have 700 out of the 1,000, which have complete information, so which we can call actual responses. So not all of them will be giving the actual or the proper responses. So again, you understand that that is the actual response. So if this is a graphic representation of the subsetting or the nesting, if I can call it, then the first part outside is the frame error. Right? The frame error. Because of the frame, how representative is the frame of the entire population? Then comes your random error or the error of chance. Okay? Probabilistic error, random error. Okay? That is inherent in the system. Okay? That is the basis of what we are doing. Okay? And finally, the last bit is the response error. That is, if you get 700 out of 1,000 that you wanted, that 300 is the response error. And sometimes response error is not just a number. It could be that they have given information. 300 families have given information, but it is unreliable or incomplete information. So that's response error. So all of that put together will be your sampling error. So your sampling error is your frame error plus your random or your chance error plus your response error. Okay. Now, error You might as well ask, go back to the first principles. I want to take you to the first principle. How much time? We have enough time. We have another hour or more. Yeah. A basic idea. Are you convinced, just because I am saying or the books have written, that there must be sampling error? Okay, it's as philosophical and deep as, the Buddha saying there is misery in the world. Okay, you have to believe it. Is it that? Or can we test it? So that is what we're going to find out now. So it's a simple numerical understanding. It's a classic case which we see. Suppose, so by a simple example, I'm trying to convince you that there will be sampling error. Okay, suppose there are 4 individuals, A, B, C, D. Their ages are 18 years, 20 years, 23 years, and 25. Simple example. You can find out or calculate their average age, which is the mean. Yeah, it's not a weighted mean, it's a simple mean. And you find out that it is 18 plus 20, blah, 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 86 divided by the number of elements for 21.5 years. Probably they are final year students or something. Okay, now suppose you want to select a sample. Let's say out of the 4, I know it's very rudimentary, you are choosing a sample of any 2. Okay, out of the 4, you have access to any 2 of them. 2 is a subset. 2 can be a sample if the population size is 4, just to keep it simple. So you have to select a sample of 2 individuals to make the estimate of the whole population. Okay. So the study population has 6 elements. Sorry, not 6, my bad. It'll be 4. The study population has 4 elements and the sample size has 2 elements. Okay. So to give equal chance to every element, okay, equal and independent chance of their being selected in the sample, we use the theory of probability to form pairs. We are basically combining. Think of permutation, combination. How can I choose a team of 2 out of a possible pool of 4? Well, obviously, there are 6 combinations. Okay, the study population has 4 people, but the number of combinations possible is 6. A and B, A and C, A and D, and then you go to BC, BD, CD, right? That's the maximum number of combinations that you have. So then each of the combinations, think about this now, each of the combinations has a 1/6 chance of being selected into the sample, right? That's why they are equal probability and independent probability. Now, the sampling error, if you go ahead, for all these 6 possible combinations, let's calculate and find out what is the average age by these pairs, because the pair has become my sample now. So I've just worked it out for you. A plus B will be 18 plus 20 by 2, 19 years. Second is 20.5. Third is 21.5. Fourth pair is again 21.5, if you see on the screen. 5 is 22.5 and 6 is 24. Well, we had estimated by the mean, saying that average should be 21.5. Okay, but we see that in most cases, the pairwise average, okay, is different. So in my sample, the first line is a 19.0 is a sample statistic, isn't it? And this sample statistic, so we'll say because this pair is on an average 19 years old, the whole population is 19 years old. But actually we know they are 21.5 years old. So there is an error that goes to prove it. And the sample statistic itself is going to be different for each possible pair. So you compare all of these 6 with the population parameter found, because we found it as the statistic and we inferred that the whole population will have an average of 21.5. You'll see that in only 2 cases, the third pair and the fourth pair, it is an exact and a very good estimation with no sampling error. But there is a difference in the other 4. Okay, the size of the sampling error also varies. Had we picked There was an equal chance to pick pair 1. Had we picked that, okay, it would have given me an error of 2.5. Because the real answer was 21.5 and I predicted 19. If I picked up the 6th pair, as you can see on the screen again, I would have overestimated by 2.5. So that is also the error. So plus minus 2.5 from the estimated or the predicted outcome, which is the mean. And pair 2 and 5, if you see, they are away or apart, okay? But, okay, they have only a sampling error of 1, right? It should have been 21.5, but it has come out to be 20.5. So there is a chance of this error going here and there. And if we are to estimate how long can we go, then we should actually give 2.5 because that's the maximum I can go. Beyond that, I cannot. So take a deep breath. Try to extrapolate this idea itself into a larger population. We'll do that with an example eventually, and you will get the idea of sampling and sampling error. So here I'm trying to prove to you that sampling error is almost inevitable. In most cases, you will get it. And thus, you have to find out a way. So, just a few relatively formal way of saying this. Sampling error is thus the error in our estimation caused by the sample itself. It is the difference between the statistic and the parameter. That is, the sample characteristic and the population characteristic. It is inevitable, almost inevitable, since a sample is a limited, incomplete subset of the population. So conceptually, it makes sense that, yes, boss, we didn't go to everyone, but we estimated with some. Some bit error might as well have occurred. So conceptually, realistically, it is possible for us to conceive it. But here comes an important. This sampling error is not a systematic error. It is a random error. It happens by chance. And this chance is automatically there in the whole proposition, our hypothesis, that if we take a subset, we can still relatively accurately predict what is happening to the whole population. But this is random error. It is not systematic error. Random error cannot be eliminated. It can be minimized and it can be estimated how far it is wrong. But what is systematic error? Systematic error is in the way that we choose the sum. Very important, pay attention to this. Systematic error is in some way or the other, knowingly or unknowingly, the way that we chose the sample and the way that we did the sampling design was erroneous or relatively erroneous. That is a systematic error or a systematic bias. That is what we have to try to avoid by good sampling design. I repeat, random error is inevitable. We try to minimize it, and we can also estimate how much will be the error. But systematic errors are difficult to identify. Where did I go wrong? Which assumption did I take wrong in my logic? Which procedure did I do wrong in my sampling design, in my research design? That is systematic error. In that error, we should try to avoid as far as possible and thus minimize. That is what we are trying to do by good sampling design. So we can estimate how large the sampling error can be based on the sample size and the concepts of level of significance and the confidence level. Okay, technical terms, I don't want to get into this, otherwise I'll overshoot my time badly. I don't want to do that. You'll get to know of it in the next 2 sessions for sure. So that is sampling error. The non-sampling error is the error in estimation due to causes other than sampling error and is somehow related to the procedures used, which I talked about. Systematic biases, systematic errors. Okay, there can be sampling bias. Okay, there can be a systematic overrepresentation of the population. There can be a systematic underrepresentation of the population. All of these we should try to avoid, and that is the learning and the theory of how to do good sampling design. Error due to non-response, which is what I said, actual responses are not identical to the entire sample. Error due to non-response, there may be refusal, there may be non-cooperation from the respondents. There may be dropouts, actually giving you an interview or a questionnaire, and the last four, they just drop out saying that I don't have any more time. There may be incomplete or invalid data forms and stuff like that. So those are errors. These are system errors. These are in our control. We should be able to eliminate. Okay. And before we actually get into an example, I want to go into a relatively elaborate example, which will tell you the different methods and all of that, instead of saying that in theory. Okay. So, but before that, very quickly, 3 important principles of sampling. First one I've already said, like Buddha, there is misery in the world. There is sampling error. Okay. The other one that we know in our field is, say, disaster management or earthquake resistant buildings. First thing we say about the basic design principle, you cannot avoid earthquakes and they will keep on coming, but you can minimize the damage done by them. Similarly, we have to design the sample in such a way that it is disaster resistant, okay, in every sense of the term. The first principle is that there is sampling error. In most cases in sampling, just read it, there will be a sampling error. And we know what it is. It's the difference between the sample statistic and the true population mean or population parameter. Okay, this is attributable to the selection of the units in the sample. Okay, so here is the example. And if you see, this is the same example we did. Okay, the difference between 1 and 2, the predicted value for each of these pairs, each of the possible samples we've taken, we had predicted 21.5 because that was the mean. But we found out that the statistic was 19, 20.5 and all of that. So on the right-hand side, there is a difference. We have proved that there will be sampling error. Second important one is, again, very easy to conceptually understand. The greater the sample size, less is the sampling error. If you take more pains, you have a larger subset of the whole population, okay, the less is the sampling error, okay. The larger the sample, the more accurate will be the error. Okay. So here I don't want to get into it, but I think conceptually you'll understand. So very quickly, instead of, we took samples of 2, right? Now we are trying to prove that if my sample size is larger, my error will reduce. Can I prove it? Yes. Let's say instead of taking 2 as a sample, I've increased the sample size to 3. So if I take a combo of 3, there are 4 combinations possible, not 6. A plus B plus C, A plus B plus D, blah, blah, blah. And then we find out the average of these trials, right? So then if you see the table here, it's worked out. Similarly, the population average for each of the 4 possible combinations is 21.5, but the sample average, as we see in the first line here, where my mouse hovers, is 20.33. The second one is 21, second one is 22, the third one is 22, and the fourth one is 22.67. So if you come to the difference on the right-hand column is your sampling error. You'll see that the first one is minus 1.17. In our earlier case, with the 2 sample size, we had minus 2.5 and a plus 2.5. Here we have minus 1.17 and plus 1.17. Have we not reduced the sampling error? We have. And how? Because we increased the size of the sample. Okay. And the third one is, again, not too much in our hands, but still, the greater the population variability, the greater is the sampling error. Okay. That's also very easy to conceptually understand. That if I'm trying to see a population which is relatively homogeneous, Okay, not vary the variation between, let's say, in the family income thing, the poorest of the family and the richest of the family. If there is a huge variation, then if the sample size is the same, also the sampling error will be large. Easy to conceptually understand. And if there is less variability in the population, inherent in the population, we don't have much to do about it. Okay, if there is more homogeneity in the population, they are relatively similar to each other. Let's say you have gone and seen a population not of a city, but of, let's say, a condominium. Okay, a cooperative society with, say, 500 families living there. But the fact of the matter is, all of them, after all, afforded to buy a flat there or rent a flat there. So eventually, you are probably talking about the middle class or the higher middle class or something like that. So there the population variability is less. So with the same sample size, 20%, let's say 20% or 10% of the whole population, same sample size, 10%, 10%, the sampling error will be lesser if they are more homogeneous. Yeah. There's also another example there, very quickly. Slightly different data. Let's say we take those same 4 individuals. No, not those 4. Different set of 4. Okay. And their ages, they differ widely. Okay. The youngest is 18, where the oldest is 40. Range is higher. So the variability is more. So if you do the same procedure, selecting 2 individuals first, making a 2 sample size, and then making a 3 sample size, then you'll find that the difference in the average age, the sample size, is 2. It varies between -7 and +7. Okay, I haven't put the table here, but essentially what you will see is that because the age differences are larger, okay, your sampling error would have come as 7, which is much more than the earlier one, which was 2.5. If we increase the sample size, made it a sample size of 3, it is supposed to come down from a smaller sample size. Yes, it is done. So again, if I had calculated with a sample size of 3, the error will still be plus minus 3.67. In the earlier case, it was minus, if you recall, plus minus 1.17. Okay, so it is proved here that the greater the population variability, the greater is the sampling error. This is because the greater range in the age of the 4 individuals, sampling population in this case that we've just done is more heterogeneous with regard to age, and so the sampling error turned out to be more. So these are the 3 important principles. First, there will be sampling error. We cannot avoid it. Second, the larger the sample size, the less is the sampling error. And the third one, if there is greater population variability, then the sampling error is larger. These are all very easy or conceptual to understand, but I tried to take very simple classic examples which are numerological. Okay, numerical, I'm sorry. Okay, so now, how much time we have? 40 minutes. Okay, we'll quickly go through the types of sampling, and then I still want to spend the entire half hour, if possible, on that example, okay, which will help you operationalize the whole idea. So you have random sampling and you have non-random sampling. Random sampling is also called probability sampling because essentially it is based on randomization. We've talked about equal and independent. Within random sampling, there are most commonly 4 sampling methods. They are simple random sampling, systematic sampling, stratified sampling, multi-stage cluster sampling. Now, trust you me, I had slides which had formal definitions of these 4. Okay? They were made earlier for some other work. When I went through that last night, I realized that it'll be too mundane and it'll be too boring for you. And you guys are probably of a higher intellect level or higher educational attainment level than that. So we'll just do it with the example. that we'll do, right? So just remember these four major types of random sampling. And then you have non-random sampling, which we can call non-probability sampling. There also, they are essentially broadly, there may be new methods, okay, but broadly four methods: convenience sampling, also called accidental sampling. We'll give you in the example. Purposive sampling or judgmental sampling, snowball sampling, and quota sampling. Okay, so just take a mental snapshot of this if you aren't already taking screenshots of this. This is what we will learn through the example that I'll do. Sometimes, of course, mixed sampling is used, which is a combination or a hybrid of the earlier categories, or you pick and choose. And it's also sometimes that, let's say, in the fourth one of the top list, multi-stage cluster sampling, we use systematic sampling also as stages. We'll see that in the example. So very quickly, basic concept of random sampling is that each element in the population has an equal and independent chance or probability of getting selected into the sample. Okay, we are trying to reduce what is called selection threat. That there's a threat that I chose the wrong people or the wrong set of people. Okay, that is the basic concept. So equal chance implies that the probability of selection of each element in the population is the same. If out of 20 people, I can randomly choose 3, then each person has a 1/20th probability, a non-zero and an equal probability, 1/20th, because there are 20, okay, of being selected. And independent, just because 3 is chosen does not mean 4 will not be chosen. Okay, so the idea is that independent implies that the probability of selection of one element is not dependent on the selection of another element. Whether another element, however related it is to the first element, is included or excluded, that does not matter. What are the major advantages, obviously, of random sampling? And that's why we are getting into quantitative and statistics. Inferences drawn from them can be generalized to the total population. Well, that's the whole idea of sampling. So it can be better generalized for the total population. Statistical tests based on theory of probability can be applied to them. Okay, we can minimize error and we can predict how much error. They are ideally suited to establish conclusive correlation. Okay, that is another type of study. You'll study correlation and regression. I'm sure it'll be touched upon today itself, if not in the entire FDP. And the major advantage is these samples, these random samples, are not biased by other conditions, such as personal preference. Very important. Personal preference, convenience, okay, using too much buddhi and own judgment, all those are system errors. Okay, but if it is a proper, true random sample, which we should do, okay, with the help of random numbers, is essentially unbiased. Quantitative research mainly or should mainly use random sampling methods, not that the others cannot be or will not be used. Okay, so methods of drawing a random sample, you can have a fishbowl draw, which is essentially like a lottery. If the population size is small, this helps. Just put the numbers of each element using separate slips of paper and put them all slips into a bowl and then pick them up without looking till you reach the desired sample size. If I wanted 5, I'll pick up 5. When I pick them up, I can pick them up, I'll not get into this, with replacement or without replacement. Once I pick up 3, I don't put it back. That means it's without replacement. But if I pick up 3 and then I note 3 and I put it back, then it is with replacement. So I'm sure you can understand, without replacement, if I pick up 3 had a 1/20th probability out of 20. But when I pick up the next one, which is maybe 8 or 9, it will have a 1/19th probability. And when I pick up the third one, it will have a 1/18th probability. So the probability will keep decreasing. It's not equal. Okay, but still there are ways to do it. And with replacement is you replace it each time, you make a note of it, but you replace it. Then the advantage is that each time, each pick will have the same probability 1 by 20, but there might be a threat that the number 3 is selected twice. In that case, you have to have more in the sample size to start with, so that some of them, okay, 3 or 4, something may be repeated. So those are little things that you might need to do. Apart from a fishbowl lottery, most importantly, there are random number tables, which most books on research method and statistics have still. If you read books, you don't read books, but I think it can be available. Actually, you don't need them because you have computer-generated random numbers. Even your smartphones will give you random numbers. Let's say we say that choose 200 random integers between 1 is to 50,000. So from a 50,000 population, it will give you random numbers, but they are all numbered. Okay, random 200 number. Okay, so that's how you draw a random sample. If it is a non-random sample, non-probability sampling, this is predominantly used in qualitative research. It does not follow the theory of probability in the choice of elements from the population sample. So it's not that we don't use it in quantitative, but we do use it in quantitative, but eventually we have to be very careful about the system bias and the systematic errors which we can do. What is systematic errors? The way that we perform the experiment. That is something that we want to minimize. That's why we are getting into it. So here the selection of the elements in the non-random will depend on other considerations, such as the preference of the researcher, the convenience of the researcher. Yehi mila, isliye main kar diya. Or the judgment of the researcher. Okay, so there is some system error which we can try to reduce by various logical ideas or having more data or something. And non-random sampling is used when the number of elements in a population is either unknown or cannot be individually identified. Okay, if I say that, boss, I have no idea, it's not trying to find out the average family income of a city, but of a region or something like that. The region itself is not well defined or something of that sort. So that is helpful when the whole population is not defined properly. It is used when the sample size is not predetermined. We don't know how many. We'll go on till our resources allow us or something like that. There also we use non-random sampling. We continue to keep on taking more samples to increase the size of our sample till we reach the data saturation point, or we are satisfied that this sample size is good for us. Yeah. So very quickly, I'm into my last half hour, and my next speakers are here. My dear students and friends, Bijoy and Shailendra. Good to see you. Very quickly, factors affecting the inferences drawn from a sample. 2 factors influence the degree of certainty about the sample. I'll go very quickly. You don't need to pore over it. The size of the sample, we've talked about it. As a rule, the larger the sample size, the more accurate the finding, and the extent of variation of the sampling population, that variance also we've talked about. In technical terms, and this will be elaborated in the next sessions, I'm sure, the greater the standard deviation, the higher the standard error for a given sample in your estimates. And as a rule, the higher the variation with respect to the characteristics of the study population, that is, if it is a more heterogeneous population, the greater is the uncertainty. So it's a repeat of what we've said. So for heterogeneous populations, you need to choose a larger sample size to be relatively more accurate. Aims of selecting a sample. When you select a sample in a quantitative study or a qualitative one for that matter, what do you aim? You aim to achieve maximum precision in the estimates within that sample. You aim to avoid bias in the selection of your sample, system bias. Bias in the selection, as we've said, and I repeat, sampling, when it is done by non-random methods, there will be system bias. because it is unconsciously or consciously influenced by human choice. Okay, the sampling frame, the index or list or the population record, which is your starting point, that may not cover the entire sampling population accurately. Okay, a section of the sampling population will be impossible to find. So your actual responses will be lesser than your sample. All of these things we have discussed. And before we get into the example, a quick one, how to determine sample size. Remember, the greater the sample size, the more accurate is the estimate. But where do we draw the line? Where do we stop? At the end of the day, like I said, there are established benchmarks for different research areas. Okay, if you are doing for transportation, maybe you are trying to find out a certain level of certainty, a certain level of confidence. But if you are doing it for rocket science, it might be very much more precise. If you are doing it for preference of food types, then it will be much varied. Okay, so once we know that, how do we determine sample size? It essentially comes down to going by general research standards. It may be 2%, it may be 1%, but lesser than 1% is often very difficult to establish that it is statistically significant. The sample, at the end of the day, the sample that you took, okay, we also have to say, we have to prove that we chose the sample systematically and the sample statistic is statistically significant. Okay, that may be difficult to establish. Okay, so broadly speaking, for quantitative studies, choose a sample of optimal size, that is, as large a sample size as is practically feasible within the resource limitations. For qualitative studies, the question of sample size is less relevant. The quality is more important than the number. It can vary on a case-to-case basis. You usually keep collecting data till you reach that data saturation point in terms of discovering new information. Okay, it might just be I'm talking to a number of people with structured interviews, and as I get more data, I will keep it. But after a while, after doing 100 respondents, I'm seeing that the next 10 are not saying anything new. So that's like data saturation. In quantitative studies, particularly correlation studies, we consider at what, and I'll touch upon it and go to my example. At what level of confidence we want to test your result, finding or hypothesis, that is the level of confidence, with what degree of accuracy we wish to estimate the population parameter, what is the estimated level of variation that is allowable or standard deviation with respect to the main study variable in the study population. Yeah. So here is an example to explain sampling design. And as we go through the example, of course, I'll take semi-hypothetical situations and try to essentially explain to you what are the 4+4, 8 sampling methods that we just named. Okay, let's say the hypothesis is there is a high prevalence of malnutrition among children in the Sundarbans. Read it, ideate on it a little bit, and we'll start. I need 1 minute break because I will change now, and I will probably try to use my writing pad. So I will change from a PowerPoint to a PDF. Just give me 1 minute. I'm trying to share from another device. Can you see my screen?
Yes, sir.
Okay. Okay. So, hypothesis, there is a high prevalence of malnutrition among children in the Sundarbans. Okay. So at first, we will have to operationalize the research. Okay. Before I get into the sampling methods, I need to just recap. I'm not sure if you've actually covered this. Maybe you have in the research design, but I will still take you through this example. Okay. Operationalizing the research. Okay. So what I mean is, what do I measure? What do I measure? I measure malnutrition. So if you remember the first lecture that we gave, okay, let's say this is the area that we want to work on. Let's say not the broad, but this is the sub area that we want to work in. So malnutrition, okay, now this has to be narrowed down. Okay. First thing about operationalizing a research is to take a look at the hypothesis. Hypothesis can be universalistic or it can be particularistic. What does it mean? An example of this is, okay, people suffer from malnutrition. That is universalistic. Everyone, are we talking of all the people living in all the countries of all times, dead, alive, to be born? That is too universalistic. So we have to converge towards a more particularistic. That means we may then say that no, we are not talking about everybody. We are talking about people in the Sundarbans. And I would imagine you know Sundarbans. It's that marshy area at the south of West Bengal and Bangladesh. Okay, the Bay of Bengal. It's marshy and it's famous for its Royal Bengal tigers. Okay, but people are poor and actually children suffer from big malnutrition. Okay, so Sundarbans is actually converging or limiting the research to a certain geographic area. And not just that, okay, maybe we are more interested in the children. So we don't want everyone living in Sundarban. We only want the children living in Sundarban. So there also we have made it from the universalistic to the particularistic. We can add another layer saying that we are trying to measure malnutrition among children in Sundarbans in the last 5 years. Maybe it was much worse 30 years ago. I am only measuring for the last 5 years. It may be it is related to some government scheme which will eventually try to do something about it. So I'm not getting into it, but the objective of the research, why are we trying to measure malnutrition? Maybe because finally we want to have a policy that we have a midday meal, and if we combine it with, say, school enrollment, then people or the kids will get better food, and thus the malnutrition degree will come down, and so many other things. So what is it that you finally want to infer from here? Whether it's a deductive logic or an inductive logic that you use, okay, is up to you. We are not getting into that part. But all I'm trying to say is, when you are operationalizing a research, you are essentially going from what to measure to how to measure. From what to how. And then, now this malnutrition itself, it is not an abstract concept, but it's a complex or compound kind of a idea or a state of health. Now, to be able to properly measure it, we need indicators. So we are not able to measure malnutrition directly. We are able to measure its indicators. Okay? What to measure? So from a concept, you are going into indicators. And indicators in this case I will just take the help of WHO, that is World Health Organization, and they have said that there are three indicators that need to be measured. One, say, is stunting. One is called wasting. And the other is weight or underweight, as they call it. Okay. Now, I have to again operationalize these indicators. What do I mean by that? That I have to first know or define what is stunting. So, stunting is nothing but height to age ratio. That your age is 7, you should have been about 4 feet tall, but you're actually much lesser. So it's the height to age ratio. What is wasting? Dubla patla. Okay. So it is essentially height to weight ratio. Okay. He's tall, but he's very thin. The weight is less. So that is a distinct indicator. So wasting is thus distinctly differently defined from stunting. And what is underweight? Then isn't underweight the same as wasting? No, not really. This is the weight to the age ratio. That if you are 9 years old, then you should be probably about 28 kgs or 30 kgs or something. So what we are seeing is, by these indicators, from these indicators, then we are getting our variables. So from concept here to indicators to variables, we are getting variables. In our case, our variables seem to be age, seem to be height, and seem to be weight. And all these are our independent variables by which we will find out these are our x's, x1, x2, independent variables by which we'll find out our dependent variable, which is malnutrition. Okay. So, and okay, let me just touch upon what kinds of variables there are and how to measure. How to measure is the measurement scale. And then we'll come to whom to measure. I'll go to the next slide. Again, to measure malnutrition among children in the Sundarbans. So the concept we've talked about, how from the concept of malnutrition, we have these three indicators, which is stunting, which is wasting, and which is underweight. Okay. Now, what are the variables? Like we said that the variables are age, height, and weight. Okay. And what are the measurement scales? So types of variables, very quickly, it is important for you to understand. Okay. Is classified based on causal models or research design or measurement unit. There are ways to classify. Okay. In one way of the causal model, what is causing and what is the effect? You have the independent variable. The independent variable is the X variable. You can call it the input variable if you want. Okay. This is the predictor. This is your age and height and all of that. Dependent variable is your Y. That is your malnutrition. I'm sorry if my writing is not so good. And then you should be careful about this, that finally you have your X's which lead to your Y. But in between, there might be some other variables which directly affect this relationship of X and Y. They are linking or intervening variables. Okay. Example, well, whether how heavy or how tall or a boy or a girl is may depends on the parents. Their height, their weight, are they fat people, are they tall people, are they short? It may depend on the per capita income. Because if you are earning more, maybe you give more nutrition. There might be some kind of a correlation between these. So these are the linking variables, which we may or may not measure. But sometimes we do measure them. They are called confounders, because if you do not, or if you rather keep your eyes closed on it, okay, then you might get wrong results. So you should be aware of your confounders. And if you want, you can measure them. And finally, extraneous variables. Extraneous are those variables which have an impact, all right. Extraneous. They have an impact, all right, but we cannot measure them, or we don't intend to measure them. Examples, all said and done, whatever the parent is, whatever their income is, whatever their age, whatever, the inherent metabolism of the child must be affecting whether he is malnutrited or not. Another example could be, let's say, sports. Okay, are they engaging in physical activity? Is that boy or girl engaging in any kind of sports activity or something like that? That may affect his physique. So these are extraneous. And then the second category is, we can also divide variables by type. You can divide them by research design. You can have active variables or attribute variables. Very quickly, active variables are those variables on which the researcher has control. Okay, the researcher can control or manipulate those variables. Okay, so control of the researcher, she can manipulate these variables. Okay, whereas attribute variables are those where she cannot manipulate. So example of this, in this one, maybe, let's say the final idea of doing this particular research on this hypothesis is to give midday meal. Okay, so an example could be that an active variable could be the midday meal itself. Okay, which is something which the researcher is able to experiment and actually control and give to the students. But attribute variable is something she cannot manipulate, which means that the example of that would be, apart from the midday meal, whatever the child is eating outside of the school, at home or outside, that is not in the control of the researcher. So that will be an attribute variable. And the third way is by measurement units. This is easy. Some measurement units are discrete variables and some are continuous variables. There are more subdivisions, but I don't want to get into this. To make a long story short, discrete variables are those which take, okay, discrete values like integers, 1, 2, 5, 7. It is not continuous. 1.12, 1.25 is not considered, whereas a continuous variable can be from 1 to 2. So it is a continuous variable. Maybe I measure it by the second decimal place or something like that. A simpler example in our case of the malnutrition of the kids in Sundarban, the discrete variable would be something like the gender. Is it a boy? Is it a girl? It's a discrete variable. Okay, maybe we can go further and say, what is the nationality of the kid? Mane, is he from India? Is he from Bangladesh? Because Sundarbans may mean, okay, India and Bangladesh. It depends on how you have put your working definition, how you have operationalized. Okay, these are discrete. He can either be Indian or be Bangladeshi or be outsider, maybe Burma or somewhere else, or Ceylon or something like that. But it cannot take continuous value. Whereas the continuous variable in our case, as you can see, age is a continuous variable. Every day it changes, by day it changes, by month it changes, by year it changes. Height is a continuous variable. Weight is a continuous variable. But we may choose not to exactly find out the age. Let's say you are finding out the age. I don't need to know the date of birth necessarily. They may not know also. I don't need to know whether the child is 9 years, 4 months, and 3 days old or not. It is good enough for me to know the child is 9 plus of age, or 8 years plus of age, or 6 years plus. So in that case, a continuous variable can be turned into a discrete variable. So for that, very quickly, there are measurement scales. I think you've already done this: nominal, ordinal, interval, and ratio. Okay. So the example, in our example, a nominal scale is essentially used to classify, isn't it? So in our example, we can say gender, boy or girl. Okay, like I said, nationality. Okay, it is a nominal scale. Nominal mean name. It just classifies, does nothing else. Ordinal scale, order, it comes from the word order, is basically used for ranking. Okay, I am not actually calculating, I'm simply ranking. For example, I don't have a way to actually measure their exact height. I don't have a tape. Okay. But as an enumerator, I am told that, let's say, 4 feet, 4 inches, or the range between 4 feet, 4 inches. This range is the average height. If he is between 4 feet and 4 feet, 4 inches, then he is average height. If he is more than 4 feet, 4 inches, he is above average. And if he is less, then, okay, he is below average. So below average, average, and above average are doing nothing. It is not necessarily telling me where it is cutting the line, but it is only ranking. Or if you are looking at schools, in the school, you may say that, okay, there are pre-primary schools, then there are primary schools, then there are, okay, secondary or middle schools, and then there are high schools. So these are examples, okay, of ordinal scale. What is interval scale? Best example is that of age. I don't really want to know, okay, what exactly is the age, let's say, because it may be too much data. So I might just say that I make some intervals, that I just see whether the kid is less than 6 years of age, or between 6 and 11 years of age, or between, say, 11 and 16 years of age, or greater than 60. So here it is ordinal, it is ranking and measurement, but not detailed but discrete measurement. And ratio scale is, of course, it will rank, but more importantly, it will measure, and it will measure continuously, which means that if I actually take the age by the days, it is almost like a continuous measurement. If I actually take the height with a weighing, with a measuring scale, or with I actually take the weight with a weighing scale, with a digital weighing scale, which will say me how many kgs, here it will say me how many inches or how many feet inches or something. Okay, these are examples of ratio scale. So having said that, we now come to sample design. I'm taking you back. We did from concept to indicator, from indicator, how we made them into variables, then how did we decide on the measurement scales, and now we come to our main part, which is how do we design the sample. Okay. So organizers, I am sorry, and especially to Shail. Okay, my dear Shail, you are the next speaker, but I think I will overshoot by about 10 minutes. Is that okay?
No issue, sir. So next session is from 12 o'clock. We have half an hour gap in between.
Okay. But we also need the coffee break. So,
sir, you go ahead. It's a pleasure to listen to you.
Shail, same here, buddy. Okay. It is a pleasure to see you guys evolve and grow. Okay. So now we come to sampling design. Within sample design also, first thing is again about operationalizing your research. Have you defined the problem? Or have you defined the population? Okay, like we had already discussed, have you narrowed it down to wherever you need to take? So in our case, as we said, have you set out the working definitions? Okay, which essentially mean the limits. So how did we define the population? We first said where? We said, okay, only Sundarbans. Sorry. Okay. Then we said, are we measuring everybody? No, we are measuring only children. So what am I doing? I am basically defining the population and converging. Okay. Then maybe trend, as I said. Okay. What am I trying to find out? Am I trying to find out about the kids who are what? Who are, say, less than 5 years old? They are also kids. Well, if I was trying to find out about child mortality, okay, WHO would be interested in this. But I may be interested in only children because my ultimate aim is the midday meal and all that. So I am interested in primary school, pre-primary and primary school. Let's say not pre-primary, only primary school. Okay. So it could be that I am only interested in primary school. So my age that I will consider is 6 to 11. What have I done? I have limited the scope to age 6 to 11. So I have redefined the word children. Not redefined, but I have defined, that's my working definition of the word children. Otherwise, it's vague, right? So age 6 to 12. It could also be that am I interested in only boys? Am I interested in only girls? Or am I interested in only both? Or both? It could also be, see, the various ways in which you can limit the scope or actually converge onto the scope. Let's say our whole idea was, say, malnutrition, but the government has told me we want to focus on the BPL because that is where the child mortality is happening. We want the poor families to get the midday meals or whatever like that, in which case, say, BPL or below poverty line list, okay, itself is the sampling frame. But have I then properly defined the population? I put a star here. Try to recall the hypothesis. Okay, there is high prevalence of malnutrition among children. If I use the BPL data, then I should reframe or rephrase it as malnutrition among poor children. So if poor is not there in my hypothesis, then this is not the right way to do it. So when you are converging also, you have to use proper logic. Okay, that is what I'm trying to say. So let's say, okay, it's now come to life, but there's a distinct lag. What do we do about this? Okay, so I will keep speaking. But unfortunately, maybe you will see what I am writing slightly later. So what I said is, why is this not happening? Okay. 50,000 kids between the age of 6 and 11. And let's say, because of the money we have and because it is acceptable as a research practice, we'll take 2% of the entire population. This is my sample size. So 2% of 50,000 is 500, 1,000. Let's say 1,000. Okay. I want to choose 1,000 kids out of 50,000. Okay? Okay? A simple random sampling would be that I have in my frame a list of all the kids between this age 6 and 11. If you think that 6 and 11, where will I find it? You can also go to all the lists that are there with the schools or what have you to find out all the kids that are there. Let's say you have these 50,000 kids and all of them are numbered. If all the 50,000 are numbered, then I can do my fishbowl method or my computer generated screen where I actually get 1,000 random kids. Actually, it is quite difficult to do because it might not be easy to number all the 50,000 kids. Okay, but okay, it can be done and it is the most statistically robust way of doing it. Second one is systematic random sampling. So it is random sampling itself, but the word systematic is coming. What does that mean? That the first sample element or unit I choose randomly. And then I use some kind of a pattern or system. Let's say I say that I will choose a number between 1 and 10 randomly, and I pick one number which is 7. Okay, and as I said in our example, let's say all the kids are numbered 1, 2, 3, 4, all the way up to 50,000 are all numbered. Okay, so I pick the number 7, and then let's say I decide that because I need I need 1,000 kids, so 50,000. Okay, so I will do 50, and I will take the number 57. I will then the number 107. Then I will take the number 157. Then I will take the number 207. Okay, and that is how I will keep a system, but essentially it is still random sampling because I randomly chose the number 7. Okay, I mean, again, we have come to the point where you can't see what I'm writing. Anyway, if you can hear me, we just actually go ahead with this. What can I do? I can see from another screen that you can't see my screen. Oh, so I'll stop sharing and I'll start sharing again. Just bear with me, folks. I'm very sorry. It's back. So like I said, after 7, it is 57, 107, 157, and 2007, and it goes like that. That is systematic random sum. Another interesting example is there of the systematic random sum. Let's say I have the numbers and I also have the names of the 50,000 kids. And I say that, okay, let me randomly pick a number, like a letter between A and Z. Let's say I pick up J. After all, I'm joining. I pick up the letter J. All kids with names starting with J, I will pick. Now here you have to put on your thinking cap, your logical cap. Now if there are 50,000 kids, okay, is the geographical distribution of all these kids dependent on their name? No. So I can say that it's a logical way to say I find out that there are 1,000 kids with J names. So I will, all names that start with J, I will take. Let's say I fall short. After all, J is not so common. So let's say J has only 400 kids. I still need to do 600. I pick another. After J, I pick, say, S. for Shubhrojit, and I see how many names will start with S, and I easily see that there are 700 names with S. So after 400, I pick the next 600 with X, and I get my 1000. That is also systematic random sampling. Okay. Now we come to stratified random sampling. I need to clean this up. Okay.
Sir, you are not audible.
I am not audible.
Okay.
Yes, sir, you are audible.
Okay. Stratified random sampling. So stratified random sampling is what? This word strata has come back. Stratum, you remember, I said were layers of some things which are common to these. Oops, why am I not sharing screen? I said share screen. The travails of online education. I'm really sorry. Okay. Stratified random sampling. So stratified random sampling is something like, okay, I can stratify this entire 1000 kids, okay, as boys and girls. Okay. This is also a simple kind of a stratification. All information about boys will be separate. All information about girls will be separate, because maybe my hypothesis is that the metabolism and the height and everything of boys and girls are inherently different. So you cannot really aggregate the information. Possible? That is stratified. And after I do this stratification, I go back to my random sampling, which I've learned in number 1 or in number 2. Or it can so be that, let's say, 50,000 kids are there and there are, let's say, 40 villages in the area of Sundarban that I have identified. Okay. I say that, okay, 40 villages are there. Let's make the strata as the village. And from each village, let us take 25 kids randomly. So what do we get? 40 into 25. I'll get my 1000. Okay. So it is stratified by village. But it is also random, because the 25 kids I chose from each village was random. That is stratified random sampling. Okay. Sometimes what happens is, you may take these kids, randomly, and it might so be that you are seeing that after all your 1000 come in, okay, let's say 500 are boys and 500 are girls. But you know that for your real population, your boys are actually 60% of the whole population and the girls are 40% of the whole population. In that case, this being equal, I can put weights onto this, and after I find my sample statistic, I can weigh this number for boys into 6 and I can weigh this by into 4. That is also an advanced way of stratified random sampling. Then we come to the final one of the random sampling, which is multi-stage cluster sampling. Now, all I need to say is that this is quite realistic, and this is what is generally practiced because it saves on time and it saves on cost. Okay. Right. Can you see my screen? Yeah. Multi-stage cluster sampling. What do we do here? We are essentially again using 2 or 3 stages of stratification. So this is a special case or an advanced case of stratified random sampling. The example will make it clear. Let's say in my first stage, okay, I say that it is very difficult to go to all the 40 villages. because physically it's a very large area. So let us do this, that out of the 40 villages that I have, let me choose 10 out of the 40 villages. And this 10 I will choose randomly. But that is a cluster. Okay, that is the first stage. The second stage, let's say, now that I have got 10 villages, okay, let's take any 4 schools from each of these 10 villages. So then I will get a total of 40 schools. See what happened in the last one here. Here in the top one, you took 40 villages, but physically it was difficult to go, but it is not so difficult to go to 40 schools because I have to go to only 10 villages. Then in stage 3, say for example, stage 3 we decide, okay, now from 40 schools, each of the 40 schools I have to pick up say 25 random kids, but that also I don't do randomly. After all, I'm trying to find out about ages 6 and 10. So there is class or grade. There's grade 1 or class 1. There's class 2. There's class 3. There's class 4. There's class 5. By the time he's here, he is 12. I'm not interested in middle school. So out of the 25, I can say I will randomly choose 5 kids from first grade, 5 kids from second grade, 5 kids from third, 5 from 4, 5 from 5. So what am I doing? I am again stratifying it. I am again stratifying this, and then I get 25. Okay, I get again 25 kids from each of these 40 schools, and then I'm able to get my 1,000. Unfortunately, again, you can't see the entirety of my screen. That's sad. Something wrong with my device. Now you can see it. So just take a look. What I did at the last stage, third stage, I took 5 from each of these 5 grades, and then I got 25 from each of the 40 schools. So what did I do? I did clustering. I did stratifying, but I did it in stages. That is multi-stage cluster sampling. Then last of the lot is when we have non-random sampling, which is something that we often use in our qualitative study or in our real life study. Okay. A convenience or accidental sampling is whatever is easily available to us. So in our example, if we announce that there is a health checkup, okay, in the 40 villages, okay, and I say, whatever are the first 1,000 kids who come in from the entire Sundarban region, okay, that is my sample. It is a random sample, is it? No. It is not a random sample because it suffers from that systematic error. That only those people who wanted to come for a health checkup, who are probably more proactive or whatever, they are the people who are chosen. Okay, so that is what we will call accidental sampling. Okay, it could also be, or by my convenience of the health checkup, or I take a car and I travel down the main highway that actually crosses through the entire Sundarban region, let's say. And then I say that I will randomly pick up 1,000 kids from here, from the houses that are on the highway. I am thinking that it is random, but no, it suffers from an inherent system bias that I am only looking at those people who are by the highway, but not taking a look at the people who are further away from the highway. So there might be a bias. Maybe people who have more money have been able to buy lands here. They are better nutrited than the others. So there is a systematic bias. But this is convenience sampling. Second is purposive sampling. It's also called judgmental sampling because you use the judgment of the research. A common example is to use experts. So let's say I go to the various experts, in this case, maybe they are the CHOs or the community health officers or something like that. And I go to them, okay, and I ask them for some information, or I ask them, since you have access to some kids in your area, okay, I have 40 such CHOs and I ask them to bring along with them, okay, 25 kids each. Okay, then 40 into 25, my 1,000 is achieved, but I have done purposive or judgmental. Okay, or maybe I say that I will only visit the doctors. Okay, I will only visit the doctors, okay, clinics, and all the kids that are coming to the doctors' clinics are the ones that I will take. There also it will be a bias because you are only measuring those kids who are right now temporarily ill or sick, and thus they might not show a right figure of all the healthy kids in the whole of the Sundarban. Yeah. Then that is two examples of the purposive. Then comes snowball sampling. Snowball is easy to understand. You ask one person to bring two friends. Then you ask the friends to bring their two friends. Then you ask each of them to bring two more, and then this actually grows up and blows up or rolls up into a snowball. Okay, it rolls up into a snowball, and more of these people coming in, that is snowball sampling. So in our example, it could be that we actually, okay, just give me a minute. Okay. Yeah, I'm sorry. So that is snowball. In our example, maybe you can say that I actually start with 40 kids. I start with 40 kids and I ask each kid to get 4 of their friends so that, okay, together they make a team of 5 and I get 40 into 5, which is, say, I get 200 such teams, and to each of these teams, those 5 people also, in a snowball method, I ask them to get another 4 each, and so it becomes a superset of that, and then I have, say, 40 of these, and then I finally achieve 1,000 kids. In some way, there is a bias because they are bringing their friends or their relatives or something, but that is snowball sampling technique. And finally is the quota sampling. A quota sampling is nothing that you actually think of all the strata that you have, and then you say that, okay, firstly, we have boys and girls. I want 600 boys and 400 girls from my sample. Then let's say I am actually going to the 40 villages. I'm going to the 40 villages, and from each of the 40 villages, I need that many number of people. So I actually break this down. So 600 minus 40 is that 15. From each village, I need 15 boys and I need 10 girls. So I'll get 25. And among the 15 girls also, then I will be able to break this out into grade 1, grade 2, grade 3, similar to what the multi-stage was. But here, I actually make up the quota and I say that I have to target these many number of people. I actually go to these people, which is my quota, and I fill my quota of the 1,000 kids that I need for my sample. Okay? Okay, thank you for your time and your patience. I'm sorry, I'm really sorry that I overshot big time.
पता नहीं, ये तो बताइए तो कंप्लेन दीजिए तो.
Okay, thank you, everyone.
Thank you, sir. Thank you so
Thank
much
you.
for your insightful and detailed, elaborate, and all very informative session. Divya, please.
Yes, thank you so much, sir, for your extensive presentation on sampling design. Now the session is open for questions. Participant can unmute yourself and ask your query, or if you want to, you can type in the chat box also.
My only request is we can also take this offline. So for the benefit of the next speakers, I would apologize to the rest of the audience and say, if you have any questions, you can definitely
Yeah, that is also very much
actually call me or WhatsApp me. And if you want to note my number, you can note my number from the organizers. It'll be easy to reach me.
Yes.
Yeah,
Yeah.
sure.
So I think we can end the session, sir.
Yes.
Okay. Thank you so much, Datta sir, for sharing your expertise, insight on the sampling design, and making us understand different terminology used in sampling design, sampling error, ways to reduce these errors, and different types of sampling method. Sir, your presentation has provided valuable information and guidance to our participants. We appreciate your time, effort you share, your experience and understanding. One more time, sir, thank you so much.
Thank you, sir.
Thank you.
Thank you.
I think our next speaker